Welcome to Chemistry 111. Today we're going to continue going through some homework. I'm going to start by finishing up going through gas part 2 assessment, then maybe go back to some of the stoichiometry. Depending on how far we get with that, we'll start looking at the old test either Friday or Monday. The plan with test 4 be not this weekend, but probably next weekend. It's all done. It's all ready. But we have a little bit of free time. I'm going to give us a little bit extra time to study and prepare for it because it's a lot of math. A lot of time to get some of those assessments done. Because some of the assessments will at least help us remind us what we need to be doing. Okay. Starting out with the first problem on the gases part 2 assessment. It's like 9 questions in this one. They're going to go through Dalton's law of partial pressures and gas mixtures. We're going to go through some density and molar mass ones. And we're going to go through maybe a few kinetic molecular theory, of fusion, and what have you, and finally some real gases. That's what we're going to do with this one. So I'll do at least 2 problems like here. Well, maybe 3. So a mixture of helium, neon, and argon are present at a pressure of 27.9 atmospheres at 28 degrees. So right off the bat, we have a mixture. The total pressure is 27.9. If the partial pressure of helium is 3.62 and the partial pressure of argon is 2.28, what is neon? So, with this in mind, Dalton's law of partial pressures is literally the sum of each individual pressure is equal to the total pressure. So, we can say that P total is equal to P helium plus P argon plus P neon. Then they giving us the total pressure, 27.9. They give us the individual pressures of 3.62. and 2.28. So plus our unknown pressure. So what do we have to do? We have to subtract the partial pressures from the total pressure to find out what is the difference. It is a lot easier than it seems at first glance. Please note, the temperature is a red herring. We do not need the temperature because the pressures are not changing. The amounts of gases are not changing. The only thing that needs to worry about is the total pressure versus individual pressure. So when I subtract the 2 pressures, I would get the difference is 22. So the pressure in neon is 22 atm. Let's check that. Boom. Okay. Now, please note, your numbers may be a little different from my numbers. So you cannot just copy 22 down and be guaranteed to get it. But the setup is going to be exactly the same for this one, or pretty darn similar. Now, this one is probably the hardest one of these guys. Reading this whole problem, if 1.84 grams of argon are added to 2.95 atmospheres of helium in a 2-liter cylinder at 27 degrees, what is the total pressure of the resulting gaseous mixture? So, they're saying, what is the total pressure of the mixture if we have pressure of helium and we're adding the pressure of argon. They give us the pressure of helium. So we need to calculate the pressure of argon. This problem combines three aspects of chemistry, three different separate problems put into one. Problem one, Dalton's partial pressure of mixing. Once we understand this one, it's not that hard. Problem two, an ideal gas equation. We need to find out what is the pressure of argon based on these values. And part three is turning grams into moles, which is classic stoichiometry. So actually, it's even earlier than that. That's like chapter 3 stuff. But these three major concepts are all going together to give us this underlying concept. So 1.84 grams of argon, which has a molar mass, if I remember right, of about 40. 40 grams in 1 mole. It might be 39.9. We're going to go with 40. So 1.8. So the first thing I'm doing is I'm calculating my moles of argon. 4 divided by 40 will give us 0.046. 0.046 moles. Now, for the ideal gas part, we have to identify our volume is 2 liters. Our temperature is, I think, 27 degrees, which when we turn that into Kelvin, we add 273. That makes that an even 300 Kelvin. So we have to say P equals nRT over volume. Our R has to be the R that turns the mole Kelvin per liter into atmospheres. So our R would have to be 0.08206. At this point, all we have to do is plug in and evaluate for this. So 0.046 times 0.08206 times 300 divided by 2. 2 liters would give us the pressure for argon is 0.566. So this is equal to 0.566. And I'm going to add that into our original equation. I know it's getting a little messy on the board now. But so the pressure of argon is 0.566. And we add that to our 2.95. And that would be our total pressure. So my total pressure that I got when I summed everything up, 3.52. 3.52. Now that one is probably the hardest of the mixed gas problem. Okay, this last one, similar to the one on that we did in the slides, but actually a lot easier. So, reading this problem, a sample of nitrogen is collected via water displacement. Since nitrogen was collected via water's displacement, the sample is saturated with water vapor. If the total pressure of the mixture is 21 degrees C, if the total pressure of the mixture at 21 degrees C is 1.68, what is the partial pressure of oxygen? So they give us, or oxygen, it's nitrogen, partial pressure of nitrogen. And they give us the vapor pressure of water at 21 degrees C is 18.7 millimeters of mercury. So we have 1.68 atmospheres equals our unknown pressure, and our P of water, which is 18.7 millimeters of mercury. The only thing we have to worry about is turning millimeters of mercury into atmospheres, because we cannot subtract millimeters of mercury from atmospheres. They are two dissimilar units, and so we need to convert one into the other. Now, because the answer is in atmospheres, I would suggest turning everything into atmospheres. It's going to save yourself some problems later on. Now, quick conversion. There is 1 atmosphere in 760 millimeters of mercury. 1 ATM. So the pressure contribution of water is not going to be a whole heck of a lot. So 18.7 divided by 760 is 0.025. So that's 0.025. So subtracting that, so you have P plus 0.025 equals 1.68. So essentially, if I round to the correct number of sig figs, 1.65 should be my answer. So there's a drop, but not much of a drop. Yes. Okay, that is a conversion that we should learn, but keep in mind, on the hints, if you clicked on the hint, I don't think I can click on the hint now that I've solved it, but if you click on the hints, that would probably give you that conversion. That conversion would also be on a useful information sheet, and I'm also going to give you, because of how I have the test set up, I'm also going to give you what would be on the useful information sheet to print off on your own or copy down on your own. So you'll have all those conversions in front of you when you do test 4. But basically, it is a known conversion that I will give you, and you can convert that through that way. The same way as I will give you that if you need it, 14.7 PSI are in 1 bar, or that to get from Celsius to Kelvin, you would add 273. I got to give you those because, memorization is no fun. Okay, this one is a standard density problem, and they ask you for the molar mass. The equation for these types of problems, it's the only one that includes density and molar mass in it, but density equals pressure times molar mass over RT. If I click on the hint, let's see what the hint would say. But it's probably just the ideal gas equation. Okay, that's not very helpful. No, it doesn't. Clicking on the hint never is a penalty. At least there might be a way for me to make it a penalty, but God, no. No. I never make that a penalty. So with this in mind, this will also be on your useful information sheet. Of all the equations you'll have on there, it's the only one that will mention density and the only one that will mention molar mass in the same equation. So they give you the density is 1.4. D is 1.4. They give us The pressure is 1.74 atm, and the temperature is 27.7. So adding 273, we get 300.7. So what is the molar mass of this compound? We are just going to plug these in. Now keep in mind, since we have to solve for molar mass, we have to get RT on the other side and P on the other side. So we're going to get the bottom to the top on that side, the top to the bottom on that side. So rearranging that equation, it looks like this. Density times RT over pressure gives us the molar mass. So multiplying everything out at this point is just what we got to do. So 1.4 times 300.7 times R, which is 0.08206, divided by our pressure, 1.74. Gives us a number that's 19.9. Yeah, R is that constant number. R depends on what pressure units we have, but it is a constant. So, and I will give you the constants. Now, please note, here's a big hint to know if you've done something wrong. What is the smallest molecule we can have? What is the smallest element? Hydrogen. Hydrogen has the molar mass of what? 1 gram per mole. Technically, hydrogen is a diatomic, so it'd be 2 grams per mole. But either way, so what does that mean? Molar mass of a compound must be greater than 1, maybe 2. If you get a molar mass that is less than 1, less than a whole number, less than 1, you have done something horribly wrong. You cannot get a molar mass that is less than 1 because that would mean it contains elements smaller than hydrogen. So if you get a small molar mass, you might want to rethink that a bit. The same way is if you get something that's in the thousands somehow, that'd be a really heavy gas, really heavy. Something maybe went wrong. It should be within a reasonable range. 100, 200 is not unheard of, but it should be less. It should be greater than 1, less than 1,000. Okay. This one is a little bit harder version of the same problem, but it's the same problem. 3.15 gram sample of an unknown gas at 43 degrees and 1.05 atmospheres is stored in a 2.75 liter flask. First, what is the density? And then what is the molar mass? So, with that in mind, we need to do a little thought process here. They don't give us the density. They give us the pressure, 1.05. They give us the temperature, 43. 43 plus 273 is going to be 316. Okay, what is the density? Oof, we don't know. But density is equal to mass over volume. Just conveniently, they give us a mass, they give us a volume. So in order to calculate that, density equals M over V, we're going to take our mass, which is 3.15, and we divide by our volume, which is 2.75. And we're going to be able to get our density. So 3.15 divided by 2.75 gives us a density of 1.15 grams over liters. Because this was grams, that was liters, grams over liters. At this point, same, everything else is the same, 316 times R divided by our pressure. And in this case, I get a molar mass, which is 28. 28.3. So 28.3, that means that guy is nitrogen. So we plug all the numbers into that equation. The density equals pressure, R times temperature over pressure. And all that equals molar mass. That is the rearrangement of the density equation. So we have to be able to rearrange the equation or to have that one already written out for us. But that is a standard usage. So we can figure out what is the molar mass of this based on density, and we can figure out if we have the molar mass, what is the density. Okay. I'm going to skip this problem. Oh, that's the hint. Oh, shoot. Whoopsie doodle. Okay. Wanted to skip. Okay. This one is a root mean square velocity. As I said, I will not test you over this root mean square velocity because there's a couple tricky traps in here. But the concept still holds true. We will look at the effusion just the same. So, what are we dealing with? Root mean square velocity. The velocity in meters per second is the square root of 3 times R times T all over molar mass. What are the tricky traps? Trap 1. R is equal to 8.314. That's a new R. That's an R that is in joules per mole, not bar liters, not atmosphere liters, but joules per mole. So we would use this one for this situation. Molar mass is in kilograms per mole. So that means whatever molar mass you would have, you would divide it by 1,000. So in the first question, they say, what is the root mean square velocity at 349 Kelvin of diatomic fluorine? So writing down what we know, we got R. T is 349. Fluorine, one fluorine is 19. So 2 fluorines would be 38 grams per mole. So in order to do this, we're going to take the square root of 3 times 8.314 times 349, all divided by 0.038. You have to make sure when you type that in that you make sure you square root the whole thing as well. If you square root only part of this, you're also going to get some other problems. So let's see. 3 times 8.314 times 349 divided by 0.038. All that gives you 229,072. Now I'm going to square root that, and I get 478.6. Really big number. your problem may have a different gas, may have a different temperature. So your numbers will maybe differ a little, but not by much. So the second one, what is the root mean square speed of helium? So helium, exactly the same. The only thing that changes is the molar mass. So instead of 0.038, we're going to have 0.04. That's the only thing that changes is the molar mass. So with 0.04, it gives us a speed of, holy cow, it has jumped up to 1,475.2 meters per second. So helium is moving at crazy speeds at that temperature. Crazy speeds. But so that one is filled with tricky traps which is why I am not going to test you over that. Even the bestest students miss those traps half the time. This one is a much easier problem. Nitrogen infuses at a rate that is blank times that of krypton under the same conditions. So the effusion is just a modification of that root mean square speed. So it's way easier. So the rate of nitrogen versus the rate of krypton is going to be equal to the square root, the molar mass of krypton on top, divided by the molar mass of nitrogen on bottom. Because they're both molar masses, you don't have to worry about the units. Are they kilograms per mole? Are they grams per mole? Doesn't matter. As long as they're the same, they cancel out. Well, I know nitrogen is 28. So what is krypton? Krypton, oof, that's a heavy one. By bromine. I have to look that up. That's one of those ones I don't know right off the top of my head. But looking at that, we have krypton 84. Well, it's 83.8, but 84. So we'll put that up there, 84. The most important thing, you make sure the square root is on both, and that we do indeed square root them both. So square root of 84 divided by 28 gives us a sum that is 1.73. Now, please note, most of these problems should have a number that is greater than 1. Greater than 1 means this is going to happen faster. If we put this in the wrong order and you put 28 over 83, you're going to get a number that's smaller than 1. So most of these guys will be greater than 1. And the last problem here is the ideal gas problem and the real versus the real gas problem. I will not mathematically challenge you to this one, but we still need to answer a question about this. So this one, it's highly suggested you look at the hint, because they have changed the ideal gas equation to solve for pressure instead of temperature, like we did on these slides. So the ideal gas, the real gas equation, the van der Waals gas equation states pressure equals nRT, all that's the same, divided by V minus NB, that's our modified volume, minus A N squared over V squared. That's, we move the pressure term to the other side. So, and we're going to need the list of van der Waals stuff in a minute. But let's look at what they give us. They give us moles is 2.4. 4. They give us temperature is 463 and volume is 4.3. And they want the answer in atmospheres. This is methane. So for methane, we have to look up what is our values of A and B. We want to find methane. Fortunately, it's at the top. So we want this value because it's asking for atmospheres. So A is 2.273 and our B, which is 0.0431. A has to do with the attractive and repulsive forces. B has to do with the actual molecular size. So they want us to first solve the real gas pressure, and then they want us to solve the ideal gas pressure, which is just P equals nRT over V. I'm actually going to do the ideal first because the ideal is far, far easier. All we have to do is take our moles, 2.4, our R, which is 0.08206, times our temperature, which is 463, divided by our volume, which is 4.3. So plugging that in, the pressure I get is 21.2 atm. Now, depends on how you want to do this for the real one. You can solve individual terms and then plug them in, or you can just plug the whole thing into a massive equation. I really don't care how you do it. I'm going to plug each term individually, and we'll solve for that and then do the math all together so we can see. So nRT, the top term in the real equation, is 91.185. So this whole thing, 91.185 divided by V minus NB. So V minus NB, 4.3 minus 2.4 times our B, 431. Our V minus NB, 4.19656. So let's working with that. Working with that, 91.185 divided by 4.19656. The whole first term is 21.7285. So we have 21.7285. But now we have to calculate what is this part. This is why I'm not asking you to do this on the test. So 2.273 times 2.4 squared divided by 4.3 squared gives us minusing 0.708. So this is negative 0.708. We'll say 08. So taking all that, if I did this right, 7, 5. Okay. Oh, 2. Really? That's in this particular situation. we didn't change the pressure by a whole heck of a lot. We didn't change the pressure by a whole heck of a lot, but we did change the pressure. So that is the all the problems for the gas chapter. With that in mind, let's find the assessment for the stoichiometry. Start looking at some of that. So, for the gases, be able to do simple pressure to volume, volume to pressure, or pressure to temperature, temperature to pressure, or volume to temperature, temperature to volume. Those simple things. Be able to do the ideal gas equation. Be able to calculate density or molar mass, given one or the other. And be able to do a simple mixing problem. Be able to do an effusion problem. And then finally be able to answer some theory questions about van der Waals equation. Nothing like super hard, but be able to recognize that equation and know what that equation stands for. Not actually utilize it, but be able to look at it and not just go, what? So hopefully if you've at least done one problem, you'll recognize that. We have some kinetic molecular theory, maybe things. Okay, so looking at this, the first problems, there's a lot of them, 10 problems, but basically these first 10 problems build on each other. So I'm not sure if you're the type of person who skips these out of order. This might not be the right chapter. Like skip around. I'll do problem 1, problem 5, problem 3, problem 8, jump around in random order. This is maybe not the chapter to do that on, because this one, it's going to do moles to moles. Then it's going to be grams to moles, and then grams to moles to grams. Just the idea. We'll build up, do something easy, and then do something a little bit harder, and do something a little bit harder on this little portion. So I may not do all of these because some of these are getting a little redundant. Okay, the reaction for producing glucose in plants is called photosynthesis. Is 6 CO2 plus 6 water goes to glucose and 6 oxygen. This is a moles to moles. If a plant produces 9.26 moles of glucose, how many moles of water would be needed? So we are setting up a ratio of moles of glucose per moles of water. So we start with 9.26 moles. I'm just going to call it the big G. And we look at the balanced chemical equation. For every 1 mole of our glucose, we would get 6. We would need 6 moles of our water. Now we would set it up. So do we multiply or divide? Well, we have to multiply. Why do we have to multiply? Because we want moles of G to cancel with our moles of G. So that is why we're setting it up in this way, in this fashion. So in this particular problem, I'm just going to multiply my 9.26 by 6, and that would give us our answer. I'm not even going to bother to solve that one. I'm going to probably skip this one, but I'm going to just read it real quick. For the chemical reaction, 2 silver nitrate plus sodium chromate forms silver chromate and sodium nitrate. What mass of silver chromate is produced from 2.37 moles of silver nitrate? So we would be turning moles of silver nitrate to moles of silver chromate and then multiplying by its molar mass. So we're going moles of A to moles of B to grams of B. And the reason a little bit harder, which is grams to moles to grams. So how many grams of silver chromate are produced by 6.67 grams of silver nitrate? So we are starting with grams of silver and working my way to grams of silver nitrate. Silver chromate. So we always start, we're going to say 66.7 grams. And 7 grams of our AgNO3. So here is where we have to do a little bit of work, a little bit of legwork. This is where we need our periodic table. Or Google, I guess. I don't know. Silver. Silver is 107.9. 107.9. Nitrogen is 14. Oxygen is 16. Might as well, since I have my periodic table open this up. And chromium, just a quick, chromium is going to be 52. Okay, I got those numbers. Those are the important numbers we got here. So, silver nitrate, 107.9 plus 14 plus 16 times 3 is 169.9. So, do I divide? Do I multiply? Well, the question becomes, what do I have here? I have grams. So I need 169.9 grams of silver nitrate per 1 mole of silver nitrate. I need grams and grams to cancel. So I set up grams on bottom to cancel with my grams on top. Then I look at my balanced chemical equation. For every 2 moles of silver nitrate, we would have 1 mole of silver chromate. So I have to divide by 2 because we want moles of silver nitrate canceled out. Finally, we got to calculate the molar mass of silver chromate. So 107.9 times 2 plus our 52 from chromium and our 16 times 4 from the 4 oxygens. So the molar mass of this guy is 331.8. So I want grams, so moles go on bottom, and 331.8 grams go on top. Okay. Not sure if you can read that on the screen. I'm going to move this camera just a pinch over. So what am I doing? I'm taking my 66.7, dividing by my molar mass to give me moles, dividing by my mole ratio to give me moles of silver chromate, and multiplying by my molar mass of silver chromate. So if I do that, funny thing is, I get 65.1 grams. 65.1. Came a long way to get not a whole lot of change in the mass. But it's a completely change in the chemical structure. Complete change in the chemical structure. Okay, looking at this. How many grams of sulfuric acid would you need to react with this many grams of aluminum? This is just the same problem. Grams of one to moles of it to moles of the other to grams of the final. So grams of A, moles of B, grams of B. Grams to moles to grams. I know that's a mouthful, but it is this generalized problem. I will go ahead. Oh, well, let's look. This one is a limiting reagent problem, trying to teach you the concept of limiting reagents. I'm going to skip that one. You can do that one on your own, but I'm going to jump to this limiting reagent problem. What is the maximum mass of sulfur that can be produced by 88 grams of each reactant? So 88 grams of SO2 and 88 grams of H2S. How much S8 could we get? So I am going to turn 88 grams of one into moles of S8 and 88 grams of the other into moles of S8. And I'm going to compare which number is smaller. This is the hard part. We're going to compare. We want the smaller number. I know the word here says maximum, but the maximum is controlled by the limiting reagent. The limiting reagent will be the one that produces the smaller amount. So when I say 88 grams of SO2, the molar mass of SO2, S is 32, by the way, O is 16. So SO2 has a molar mass of 64 grams per 1 mole of SO2. In order to make this balanced, 8 moles of SO2 is needed to produce 3 moles of S8. So how many moles of S8 could 88 grams of SO2 produce? Real quick, 88 divided by 64 divided by 8 times 3. So that could produce 0.515625 moles. Now let's do the same thing with 88 grams of H2S. Well, H2S has a molar mass of 34 because H is essentially 1 grams per 1 mole. And you need 16 moles of H2S to produce 3 moles of S8. So 88 divided by 34 divided by 16. And so it could produce 0.4852941176. Basically, H2S produces less because H2S would run out first. H2S would run out first. So the final step they ask for is what is the mass of S8 produced? So we're going to take that guy, that 0.485, multiplied by the molar mass, which would be 32 times 8. 32 times 8. And so the mass I get will be 124. 124. So the molar mass of S8 is 256. But so when you do a limiting reagent problem, you're given a mass of reactant and a mass of the other reactant. That's the big hint. You're given a limiting reagent problem. You're given the mass of 2 reagents, usually followed by what is the maximum amount of product that could be formed. But so we always use the one that runs out first, the one that produces less. So that is a tricky one. We will continue from there on probably on Friday. Let's look. I just want to look at what other problems we got. We're out of time. Yeah, we'll product of aluminum. Okay. Yeah. We will do like number, I think 8. We'll finish up with number 8 or 9 on Friday. But I'm going to skip the last limiting reagent problem and just do the percent yield problem. But that is all the time we have for right now. So hopefully that will help you at least get some of those work problems done. And we'll see you guys on Friday.